Greetings, Honors Algebra 2, Part B, Chapter 7, Sections 1 and 2. Now, yesterday we did the graphing. Today we're going to look at just the functions, how to be able to write the equation and evaluate the equation for exponential relationships. You should be able to know the general form of an exponential function, know simple interest, compound interest, for growth and decay functions, and what each variable represents when we're dealing with these situations. Kind of an idea of what we're going to look at today. So we can use this form when we're trying to graph functions. This is kind of the general parent function. We should realize what each of these variables represent from yesterday. So the awesome A value here, this determines if the curve's up or down and how steep. So if it's positive or negative, to realize if it curves up or down, the reflection, and then how steep is a vertical stretch. B describes if it's a growth or a decay. So when B is greater than 1, we have a growth, and when it's between 0 and 1, it's a decay. H is our horizontal shift, left or right, opposite what you see. And K is our vertical shift, up or down, what you see for the numbers in the equation. So when we're looking at our growth function, here is the general form for our growth function. A is still the same value. It's our starting point. It's our how we're increasing. It's our starting value. If you think about that, if R is 0, 1 plus 0 is 1, and 1 to any power is 1. 1 times A is A, so Y equals A. This is our starting value. R is the rate, written as a decimal, for how it's growing. You're adding it to the 1. So 1 plus R is the factor, and T is the time of growth. Decay is very similar, except that we're subtracting. We're going to be from smaller decaying, less amount, so we're subtracting. So A is still our starting value, R is still the rate written as a decimal, 1 minus R is still the factor, and T is still the time. So if you think about how if we had the number 1 as a percent, then it's 100%. 1 as a percent is 100% minus R, the rate, as a percent. So if you're subtracting the percent of decay, you'll have the percent left over. So the number within this parenthesis here is always like representing the percent I have. So I think about how that number here, the base, is always going to be the percent I have. And it doesn't matter if it's growth or decay, because if I'm growing 5%, I'm going to have 105%. If I'm decaying 5%, I'm only going to have 95%. So I always write down the percent I have. So if this was the equation given to us, we have to first realize it's growth or decay. How do we figure out if it's growth or decay? Is always the base. This number here is greater than 1, so I know it's a growth. What is the initial amount? The initial amount is 5,000, that A value. What is the growth factor? It would be 112%. The increase is 12%. Increasing by 12%. The growth factor is 112%. For this one here, we're going to have a decay because the base is less than 1. The initial amount here is 650. Starting value. Our decay factor is 75%. So what's our decrease? 1 minus 0.75, which is 25. We lost 25%, so we have 75%. This one is going to be our first video problem. So video problem. The video problems, you do not listen in class. These are kind of like homework assignments. You should be completing these problems. I don't usually write this down, video problems. I usually just state it orally so you have to pay attention in the video. So you need to complete these 4 questions about this equation. When you walk in tomorrow, you put it in the input bin right when you walk in the door. I'll look it over to make sure you have an understanding from the beginning part of this video. So this is the first kind of like video problem you've seen. You do get points for it. You need to turn in right when you walk in the door. It's a kind of a checking for understanding. problem. There'll be another one in this video. I'm not going to write video problem on the next one, but you need to listen orally to know when I give a video problem. Simple interest formula. So if we're finding simple interest, here's the formula for it. P is still our starting amount. A here is actually the account balance, the total. P is the beginning principal or starting amount. R is still our rate as a decimal, and T is time in years. It has not changed from the previous functions, the growth. So we can calculate this. We can do 500. So this is going to be our starting value. So this is going to be P. So we're investing. This is R, our percent, and this is T, so defining our values. It's good to write down our function with variables so we understand what we're going to work with. This is good work to show. So then we know that A is going to be 500 times 1 plus 5%, so 1.05 to the 10th power. Now order operations, what do you got to do first here? Well, you have to, and this is when I've seen an issue with students in honors algebra 2, you've got to deal with the power first. You've got to calculate 1.05 to the 10th power first. So if we do that, we find it's 814.45, and that'd be dollars. So you have 5% interest for 10 years. You'd have $814.45 after the 10 years. So here's the second one here. So 550. This is our p-value, our rate, and our time. So this one's going to be 1 plus 0.45, so that's 1 plus 0.045 to the 10th power, or 550, 1.045 to the 10th power. We have to deal with this power first. We've got to do the power. So for this one, we get a little bit more. 854.13. But really, when we're looking at how things work in real life, we really should be using a compound interest formula. And similar formula, we still have our A, our amount in the account. P is still the principal investment, our starting amount. R is still the interest rate. Now N is the number of times compounded per year. So if I'm compounding monthly, N would be 12. If I compound daily, it'd be 365. T is still our number of time in years. So know your variables, what they mean, and know the formula here. So this is a little different. You think about if our interest rate is 10%, and then we are compounding monthly, 10 divided by 12 figures out what's the percent we get for those 12 months. And then the power up here is also the amount of years times the amount of months, or how many times you're compounding a year, figure out how many times this rate would be taken, that factor would be taken. So two examples here. We still have our investment, which is our P, our starting amount, our rate compounded quarterly, so that's our N value. For 5 years, that's our T. So quarterly, what would N actually be? Quarterly means quarters, so if it's in 4 times a year, N is 4. So if we're going to plug this into our formula, 3,000 our starting amount times 1 plus our rate as a decimal, 0.07, all over 4 quarterly to the 4 times 5. So looking at how we're going to solve it, we're going to have to deal with the power, 4 times 5. Then we can do this base to the 20th power. Then you can multiply by the 3,000. So make sure you follow the order operations here. So make sure you can plug that in the calculator correctly. It's frustrating when I see people that write it right, but they just can't multiply it out. They don't follow order operations. If you do multiply this out, you get a value of $4,244.33. Now think about this. Compound quarterly means you're getting interest on the interest. That's what compound is describing. So after the first quarter, you find the interest you get. The second quarter, you're not only getting interest on 3,000, you're also getting interest on that interest you got the first quarter. And so it grows at a quicker rate. That's the exponential growth that we talk about. So second example here, we have P, our starting value. We have rate, compound monthly, so it's going to be 12 times a year, and for 7 years. So if we write that out, and you 100, and you should find an answer of $13,150.12. So nice little increase there. That's after 7 years, though. So another example, you step on a rusty nail. You have 25 bacteria cells enter into the wound. The bacteria cells divide in two every quarter of an hour. So every quarter of an hour is how fast they are dividing in two. Write an exponential model to describe the situation. How many would you have after 8 hours? So we have our starting. This is kind of our starting value here, 25. This is kind of like a p-value if you want to think about our starting value. Now our base, what's our base? It's dividing into 2, which means it's going to be doubling. Okay, so we're going to double. That's our growth factor. We're going to double the 25 bacteria. But how often are we going to do that? Every quarter of an hour. So how often would that be done in 8 hours? So if it's every quarter of an hour, it's splits in 1 hour, it's going to be 4 times. So in 8 hours, 4 times 8 would be 32 times. So that's how many times we would have doubled the bacteria. So this would be the equation to represent the situation. And so if you actually plug that in, you'd find this many cells. That's what, 107,374,182,400 bacteria cells in 8 hours. So you can see how fast infections can start. So you bought a car. Probably not this car, but if you bought a car, what happens to cars when you buy it? You drive it off the lot and bam, it already decreases in value. So here's a car, starting value 40 grand. Depreciation rate 18%. So that's how fast you're going to depreciate or lose the value. So we can write a model for this. So 40 grand are starting, 18% is our rate, or decay value. So there's our model, 40,000 times 0.82. Well, wait a minute. 0.82 is not 18%. So how do we get that value? Again, 0.82 is the percent you have. 18% is the percent you lose. So if you do 1 minus 0.18, you find the 82%. You got to write the percent you have. Not the percent you're losing, the percent you have. To the t power. So after 1 year, what will the value be? You just plug 1 in for t, 32.8. After 5 years with the value, you're under $15,000 already. So cars depreciate at quite a quick rate. So you can get quite a nice car. If it's 4 or 5 years old, you can get quite a bargain on those cars because the depreciation rate decreases so quickly. Now as it gets older, it starts to flatten out. It's exponential decay. So think about the curve of that. So it's decaying like this. So it's going to decrease really quickly, but if you buy a car over in this area, it's not going to depreciate quite as fast as here. As I say, might be a better bargain. Now in this range, you might want to figure out how old the car is and how long it's going to last. I'm actually going to make this your second homework problem, your second video problem. Maybe I'll put a VP so you know it's video problem. I won't always do this, but maybe I'll try to start doing that. So video problem number 2. So you have 2 video problems to try to answer and then turn in right when you walk in the door. So this is your first video for part B of Honors Alpha 2. Have a great night and we'll see you tomorrow.